Hello, and welcome back to Physics 141, Classical Electromagnetism 1. So far, we have discussed about basic electrostatics. In the previous chapter, we focused our discussion on the electric potential, which in Coulomb's law is given by this form. Now, in chapter 2, we focused on how to solve the electric potential, because the electric potential can be used to find the electric field, which is just the negative gradient of the potential, and in turn it can also be used to solve for the charge density by virtue of Gauss' law. So for this chapter, we will now be discussing about what happens when electric field goes through matter. And our first lesson for this chapter is all about induced dipoles. So when electric field interacts with matter, it actually induces a dipole moment in the matter. So matter can be generally categorized into two, conductors and insulators. Insulators are also called dielectrics, and we will be using the term dielectrics instead of insulators. So if you have an external electric field and you expose a conductor to this field, so what happens is electrons, since in a conductor there are free electrons, and electrons always move opposite the direction of the field, so electrons will migrate from the atoms on this side, leaving the atoms on this side positively charged, and they will migrate to the opposite side, making the atoms on this side negatively charged. And this will induce a dipole moment inside the atom, inside the conductor, which will in turn create an internal electric field. And in this case, the internal electric field is exactly equal to the external field, but opposite in direction because of the negative sign here, which means the total electric field inside any conductor must be zero. So we already established this in the previous chapter. The electric field inside a conductor is always zero. And this is just another picture that in terms of the induced dipole inside the conductor. However, if you have a dielectric or an insulator, it doesn't have free electrons. So the electrons in a dielectric are actually bound to its parent, to their parent atoms. So in this case, what the atom can do is to either rotate or stretch in such a way that it will align its positive and negative side with the external field. So in a dielectric, we will assume that there will be an induced dipole then, which is in the same direction, again similar with the conductors, in the same direction as the external field, and due to this induced dipole moment, we'll have an induced electric field inside, an internal electric field. But this internal electric field is very weak, such that the net electric field inside the conductor will be in the same direction as the external electric field. So it's no longer equal to zero, unlike the conductors. So if you have atoms, the atoms or the molecules inside the dielectric actually align the dipole moments with the external electric field through stretching. So such as this one. So the atom from a spherical, perfectly spherical form, when it's neutral, it can stretch or it can rotate. And this is generally called polarization. So basically, your dielectric now, in this case, is polarized. Atoms and molecules and in general matter can actually be polarized. Okay, so let's focus on a single atom first. If you have a neutral atom, such as this one, it has a nucleus composed of protons, positive protons, and neutrons, which are neutral. And then you have an electron cloud, rotating around or revolving around your nucleus. So if you expose this neutral atom to an external electric field, what happens is the atom will actually stretch. So it will rotate and then it will stretch until such time that the positively charged nucleus is somewhere on this side and the negatively charged electrons are on the opposite side, because negatively charged particles move in the opposite direction to the external field. But this is actually just a very exaggerated version. So the displacement of the nucleus is actually not that great. It's actually very minimal. So there will now be an induced dipole inside the atom, an atomic dipole. And this atomic dipole is actually proportional to the external electric field by virtue of a proportionality constant called alpha, which is just the atomic polarizability of, or the polarizability of the atom. So an atom with a large alpha or with a large atomic polarizability is easily polarized. So when you say it's easily polarized, dipole moment is actually very large if you expose it to an external electric field. In general, polarizability can apply to an atom and hence to a molecule. So in the case of the molecule, a molecule can be polarized in certain directions. So for a molecule, the polarizability is actually a 3 by 3 tensor. So molecules have what we call polarizability in certain direction. It can be easily polarized along this axis or along this direction, but not easily polarized in another direction. That's why, in general, polarizability is actually a tensor. It's a 3 by 3 tensor. But you can always diagonalize this tensor so that you will only have diagonal elements, x, y, and z components. So in general, the dipole moment of a molecule is composed of 3 components: x component, px, py, and pz, where px is given by this. So you use the polarizability tensors, and this is py and this is pz. Now, in the event that you have diagonalized your polarizability tensors, then these terms here will be gone, and you're only left with the alpha x, alpha y, and alpha z components. You only have 3 components. Okay, so let's have an example. So this is a primitive atom. So in a primitive atom, you have a point nucleus, positive Q, and then you have a spherical electron cloud with a total charge of negative Q. So this is a neutral primitive atom, primitive atomic model. And the radius of the atom is say A. So in this case, the radius also of the electron cloud is also A. So, and we are asked to calculate the atomic polarizability of this primitive atom. So when you expose this primitive atom to an external electric field, what will happen is the nucleus, the point nucleus will actually be shifted from the center by a distance d from the center. So in this case, we can actually, this distance d is actually very, very small, so that you can always assume that the electron cloud is not stretched, but it's still spherical. Since d is very much smaller than a, the radius of the electron cloud. So this is just we just exaggerated this one, but this is just actually very, very small. So d is very much smaller than a, the radius of your electron cloud or your atom. So what will happen now is, because of the external electric field, your nucleus, your point nucleus, will experience a force in the direction of the external field. But because the nucleus is no longer at the center, then the electron cloud will now also exert a force on this point nucleus in the opposite direction. So actually, you can think of this electric field as the electric field of the dipole moment, or the dipole created by this shift of the point nucleus, shift in location of the point nucleus. So in equilibrium, the force due to the electric field and the force due to the electron cloud will actually balance each other out, because your point nucleus will no longer be moving. So meaning the two forces, the force exerted by the electric field and the force exerted by the dipole, or the force exerted by the electron cloud, will essentially balance each other out. So in this case, the external electric field and the electric field of the electron cloud will actually be equal in magnitude but opposite in direction. Now, what is the electric field due to the electron cloud? So you can think of the electron cloud as a uniformly charged sphere with negative charges in the cloud. So how do you get the electric field of this? You use Gauss law. So you make a Gaussian surface, say a distance d. So what is the electric field at point d from the center of an uniformly charged sphere? So you use Gauss law. So I will no longer be solving this. You already know Gauss law. So using Gauss law, you will find that the electric field a distance d from the center of a uniformly charged sphere, in this case our spherical electron cloud, given by this equation. So Q, the magnitude of the electron cloud, charge of the electron cloud, d is the distance from the center, a is the radius of the cloud. So again, we will let the charge times the distance, magnitude of the charge times the distance of the dipole as our dipole moment P. And since this is just equal to the external electric field in equilibrium, so we can actually focus on this equation here and rewrite it to something like this. And if you will recall from the generic definition of polarizability, alpha times the electric field. So meaning this term here is just our alpha, 4 pi epsilon naught AQ. So 4 pi epsilon naught, these are just constant. So alpha, the polarizability of an atom, only depends on the Bohr radius or radius of the atom. So we can actually write this as 3 epsilon naught times V, where V is the volume of the atom, 4/3 pi a cube. So this is now the polarizability of our atom. So it only depends on the radius or the volume of the atom. Okay. In some conventions, they actually write polarizability in terms of a cube. So actually, since 4 pi epsilon naught is just a constant, then the polarizability is essentially similar to a cube. So A is usually what we call the Bohr radius. And this approximation of the polarizability of an atom is applicable only to simple atoms. So, and this is the classical case. We didn't use any quantum physics here. It's purely a classical calculation. That's why it's the primitive or the classical model. So these are some of the atomic polarizability of different atoms which are determined experimentally, not calculated but experimentally. So the atomic polarizability are in terms of alpha over 4 pi epsilon naught, and the unit of that is cubic meters because that is volume. So actually in units of 10 to the negative 30 cubic meters. So for example, for hydrogen, the atomic polarizability is 0.667 times 10 to the negative 30 cubic meters. Okay. So another example. So let's now go to a quantum mechanical result. In quantum mechanics, the electron cloud of a hydrogen atom in the ground state has a charge density given by this function here as a function of R. So it's rho, volume charge density is given by that one. So find the atomic polarizability of the hydrogen atom. Okay. So the Bohr radius for hydrogen is given by 1 times 10 to the negative 30 meters. Of course, the charge, since a hydrogen atom basically just a proton and an electron. So the Q, the charge Q, is the charge of the natural quanta of charge, 1.602 times 10 to the negative 19 coulombs. Okay, so the same thing will actually happen as in the previous example, in the primitive atom, even though we are now using a quantum mechanical result for the charge density. So first we need to find the electric field of the cloud. And we do that using Gauss law. So if you use Gauss law, so Gauss law, what's the electric field at point D, a distance from the a distance D from the center of your electron cloud. So use Gauss law, and basically you'll get kq over r squared or kq over d squared, where q here is the q enclosed. So the charge enclosed by this surface now is just rho times dv. Or sorry, I forgot to change our notation, but supposedly we will use tau. But anyway, the v here is not potential but volume. dv in this case, just r squared sine theta dt d phi. But if you will notice, our rho is only a function of r. So meaning, the part sine theta d theta d phi, you integrate that, that will give you 4 pi. So in simplicity, dv or d tau, the differential volume, just 4 pi r squared dr. So this is dv, this is your rho given here. So then this will be the charge enclosed. So you will encounter an integral here of the form integral of, say, 0 to u x squared e to the negative lambda x dx, and this is just equal to 1 over lambda cube 2 minus e to the negative u lambda 2 plus 2 lambda u plus lambda squared u squared. So you will encounter an integral of this form, and just use this integral formula here. Okay, you can freeze the video so that you can copy the integral formula. Okay, I'm now going to erase the integral formula. So using that integral formula, you will achieve this result for the charge enclosed. So it's actually proportional to Q. So as Q, or sorry, as R approaches as D approaches A, the charge enclosed will actually be equal to Q, the total charge of the electron cloud, or the magnitude rather of the electron cloud. So as D approaches A, charge enclosed will actually approach to the total charge of the electron cloud, or the magnitude rather, which is Q. Okay, so we will still simplify this result by expanding this exponential here. Now, if you will recall from your basic mathematics, if you have e to the x, if you can actually write e to the x as a series. So it's just x to the n over n factorial. So we will use this expansion of an exponential to expand this term here. So e to the x, our x is negative 2d over a. We will expand that and we will have this term, or this result. Okay, so we plug in back this expansion here and then simplify, and you will notice that this whole term here, whole term in the parenthesis, will just be actually this one. Will actually be just this one, the term in the parenthesis here, 4/3 d cube d over a cube. So if you have this expansion, plug it back here, the first there will actually be the first term in this product here will actually be 1. So you have 1 here, 1 minus 1 is 0, and then the next term will actually be this one, 4/3 d over a cube, and then there will be a next term which is d to the 4th over a cube. But again, from this, our assumption here is that d is very much less than a, meaning d cube is actually now very small. And how about d to the 4th? So we can neglect the powers of the higher powers of d. Okay, so we just expand up to d over a cube, and our electric field will now be, so our Q enclosed is just Q times this term here. Okay, so you have d squared here, you have d cubed, so you have d times q times d, that's just your dipole moment p, and 4, there's 4 cancel out, so you have 3 pi epsilon naught a cube. So we again write this, rewrite this equation, and we see that basically, so take note, p is equal to alpha e, And basically, this is our alpha here, 3 pi epsilon naught a cube. So this is the quantum mechanical result. So if you get the alpha, since we usually write the polarizability in terms of alpha over 4 pi epsilon naught, we divide this one by 4 pi epsilon naught, then we have 3/4 a cube. Unlike the classical result, which is just equal exactly to a cube, the quantum mechanical result is just 3/4 a cube, 3/4 of the Bohr radius cube. And if you plug in the given values, you will get a value of 0.09 times 10 to the negative 30 cubic meters. Now, if you use the classical result, if you treat the hydrogen atom as a primitive atom, so that's the classical mechanics case. So alpha over 4 pi epsilon naught is a cube, the previous result. So using the Bohr radius of this, you will get 0.125 times 10 to the negative 30 cubic meters. But if you compare it to the if you compare it to the experimental value of the polarizability, it's actually 0.667, but this is 0.125, this is 0.09. So actually the classical result is much closer to the obtained experimental value of the hydrogen atom's polarizability. So this tells us that the hydrogen atom can be treated as a primitive atom and just use classical mechanics or classical physics instead of quantum physics or quantum mechanics. Okay. So let's have another example in polarizability. So suppose you have a point charge Q and it is located at distance r, where r is very, very large, from a neutral atom with polarizability alpha. So the question is, find the force between the point charge and the atom. Okay, so the point charge will have an electric field. Electric field is actually radially outwards. So this is the electric field of the point charge. It's radially outwards. So this electric field at the location of Q will actually be in this direction. So the electric field of a point charge is just kq over r squared, r hat. So r hat here is this direction, radially outward. And at the location of the neutral atom, the electric field of Q is along this direction. So let's say that the direction is the positive z axis. So what will happen now with your neutral atom is that it will be polarized. So meaning there will be an induced dipole inside the atom. So a polarized atom is essentially a dipole. So this atom now, since this is now a dipole, it will now also have its own electric field. So it will now generate its own electric field because it's now a dipole. So this is the induced dipole moment on the atom due to the electric field of Q. It's just alpha, the polarizability of the atom, times the external electric field, so the field of Q. It's given by this one. So this is now the induced dipole moment in your neutral atom. So your neutral atom now becomes a dipole. So if you will recall, the field of the dipole is given by this form, in spherical coordinates. So I'm just gonna erase the electric field of ano. So since this is now a dipole, the electric field of a dipole It's actually something like this. So if the dipole moment is in this direction, then the electric field of this dipole is something like that. So this is the electric field of a dipole. So at the location of Q, the electric field of this dipole is actually in this direction. So at the location of Q, the electric field of the dipole is actually towards the dipole. So by the way, this r hat here is the r for the dipole, the radial unit vector for the dipole. And if you relate that with the radial unit vector for the point charge, they're actually opposite of each other at this along this axis here, the negative z axis. Because along this axis here, it's for the point charge, its r is actually along the positive z axis, but for the dipole, its r is actually in the opposite direction, negative z axis. So at the location of the point charge, the electric field of the dipole is, so with respect to the dipole, the location of Q is actually at theta is equal to pi, because we measure theta from the positive z axis from the north pole to the south pole. So this is actually pi here. Theta is equal to pi. When theta is equal to pi, cosine of pi is -1, sine of pi is 0, and you will get the electric field of the dipole at the location of the point charge is this one. So this electric field of the dipole will now exert a force on the dipole. And since we know from this equation of the induced dipole that the magnitude of P is just alpha over 4 pi epsilon naught Q over r squared, where r is the distance between the dipole and your point charge, then the electric field of the dipole is given by this equation. So we now know the electric field of the dipole at the location of Q, and this electric field will act a force on the point charge Q. So the force exerted is just Q times E. So the external electric field and the point charge Q. So Q times E. So you just multiply this by Q, and this is now the force exerted by the dipole on the atom. If you try to solve the force exerted by the point charge on the dipole or on the atom, you will get a similar result, but the direction will be negative. So take note, the Newton's third law of motion applies here. The force exerted by the dipole on the atom and the force exerted by the force exerted by the dipole on the point charge is just equal in magnitude to the force exerted by the point charge on the dipole, but they are opposite in direction. So since we still haven't discussed the force exerted on a dipole, then that is why we are trying to solve the force exerted on the point charge due to the electric field of the dipole. So this force is actually attractive. So they will pull each other towards themselves. So equal in magnitude but opposite in direction to the force exerted by the point charge on the dipole. So in the future lessons, we will be discussing about the force on a dipole. So we will try to verify these results by solving the force exerted by the point charge Q on the dipole. So take note here, the force exerted by the dipole on the point charge Q is along the z hat direction, so in this direction. So the dipole will pull the point charge towards it. So it's an attractive force. Okay, so that is the end of this lesson. So In the next lessons, we will be discussing uh, the force and torque on a dipole. I will see you again in the next lesson.